Okay, so what we need to do today, we're just going to finish the complex numbers. It shouldn't be too long. Let's look at an example. I always write down the definition of I. That's a good place to start. I, okay, is the square root of minus 1. Okay, and everything comes from there. So a complex number is made out of real part and imaginary part. Now we just had a discussion about one exercise, and I myself kind of forgot. Obviously, the real part of Z is 3. If they ask what's the imaginary part, I am. And as Olivia mentioned in the textbook, it looks like LM, okay? But it's not, it's I am. The imaginary part is the constant or coefficient of I. It's 4. It's not 4I, it's 4. Okay, if they ever ask you what's the imaginary part, it's 4. It's the coefficient of I. Now, what we can see here, this is a good starting point for us today. A complex number is really described by two numbers, right? The real part and the imaginary part. Can you think of another thing, a creature, mathematical creature, in physics that exists as well, that is defined by two numbers? You need two numbers to define. So I'll explain. Normally, when you have a number, let's say speed, you just need 50 meters per second. You know, you just need one number. But there are a whole different class of things in physics and in maths that you need actually two numbers to define. Vectors. That's it. Okay. All right. So you know, if I have something like this, okay, and this is, you can say the x and the y, the Cartesian plane. Okay, it will have a coordinate 3 or 4, and then okay, later on you already learned about vectors. Okay, you use a coordinate. You start, you put the bum in the 0, in the origin, you put the arrow at the tip on that point, and voila, you got a vector. Okay? It's defined by its x component. Do you know when I say component, you know what I mean? Okay? That's your x component. It's basically, what's the x component? 3. And it has a y component. Okay? Which is 4. Okay? You can also define it in two different ways. You can say, okay, vectors all have a magnitude, which is the left, and the direction, which we normally use as an angle from the x-axis. Okay. Well, now we can just combine the two things and say, okay, instead of calling this x, we call it the real part of this complex number. Okay. So the x component is the real part of the complex number, and the y will be the imaginary part of this number. So a complex number 3 plus 4ia, 3 plus 4i, I don't know where a comes from, okay, 3 plus 4i is basically meaning that it has a real part, which is 3, and imaginary part, which is 4i. Okay, your y-axis is like you're counting in i's. Okay, so now we have, you know, now we suddenly realize, okay, all the numbers we were dealing with them in core maths were just on the x plane. Think about it, all the numbers, the integers, the rational, the irrational, whatever you want, they were just on the x-axis. And all we did now, when we opened it up to complex number, we moved to the plane. Now we suddenly have points above or below the x-axis, which include a certain imaginary part. Okay, I'll just pause here for a second. So yeah, it's just another way of looking at it. Just another way of looking at it. You can say a complex number, oh, it's just a vector. Okay? It's important to know this is not the y-axis, it's not kind of function. We don't have function here. The y-axis is not a function of x like we normally have. It's just a certain point. Now we'll call that z1. Okay? Z1, because we're going to add a few more, because this is Z1, okay? Now, let's look at another number. We can do the complex, I forgot to remind you how to conjugate, the complex conjugate. The complex conjugate of Z1. What would that be? If we're just looking at that, forget it. 3 minus 4i, okay? Now, yeah, I should have said this kind of picture, this way of representing a complex number is called argand. Some kind of French guy who thought, he's the one who came up with this idea, oh, you know, complex numbers are basically numbers on the plane rather than just on the line, okay? so let's try and draw Z1, the complex conjugate. So it will have the same component, right, of x, but it's minus 4i. So what can you how can you describe that? What's
It's a reflection.
It's a reflection over the x-axis, exactly. The angle here and here is the same, absolutely. Let's just do one more. Let's just do a Z2. So we'll just, let's say, minus 2 plus I. Okay? So let's try and draw it. What will be the x component of this Z2? Minus 2. So we're going to try, if this is 3, so we'll say minus 2, let's say. And what will be, okay, I decided to do one without a number. What will be the imaginary part? 1. Okay, so it will be, yeah. So this is going to be Z2. Okay, and obviously now we can also look at the complex conjugate. Okay, before I even draw it, you can see that, okay, it's going to be like this, like Rachel said, a reflection over the x-axis. Okay, and now we can also draw it. It will be minus 2 minus I. Okay, so that is Z2 complex conjugate. Okay, I'll pause again. Okay, so yeah, so what we, as you said before, we said we can describe a vector with the component, or alternatively, we can represent a vector with the side and the angle from the x-axis. So that might mean, if complex numbers are like vectors, then maybe there's another alternative way of representing a complex number. Instead of the two components, maybe we can have a size of the complex number and some kind of angle from the x-axis. And that's what we're going to do now, okay? So the size is called the modulus. Modulus is the size, and we give it a symbol like that. It's like the absolute number. It's the same sign, but it's not the same thing, but it's the same sign, which is a bit confusing. How do you reckon we can calculate the size of this specific complex number, 3 plus 4i? If I know that 3 is the x component, 4 is like the y component, how do I calculate sizes of vectors? Remember?
Oh, it's Pythagoras.
It's Pythagoras. If this is 3, and really this is 4 as well, so what do? Square root of? Okay, if this is 4 and this is 3, how do we find the size of that one? It's fine, you're right. Sorry, I didn't hear what you said, but obviously I chose easy numbers. So how do we do it? 4 squared plus 3 squared and square root of that. Okay? And you're right, you chose easy numbers, it comes out as 5. Okay? But let's just write, let's write that down. If I have Z equal A plus BI, I'm just going to do it at the same time. So I've got general now. Instead of 3 and 4, let's say A and B. How would I find the modulus? It will be the square root of A squared plus B squared. Okay, so that's the modulus of Z. The size of the complex number. That's a weird thing. What does it mean, the size? Okay, it only makes sense in this kind of in the representation.
So modulus is size.
As a size. It's like the length of the vector.
Yeah.
Meaning the argument will be the direction, okay? And we always measure the angle. The convention is from the, what do you call it? From the x-axis, okay? So I just want to see what sign, just pause here to see what's, okay, so yeah, the symbol for argument is argz, okay? Did I put brackets for it? Yeah. How are we going to find this angle? If I know the components.
You can find out the gradient and then use tan m equals.
You could do that, but you're going like around the loop. You straight away trig, like basic, first trig, okay? Okay? Tan, I can say, well, this is the angle, right? Argz is that angle. How do I know what the angle is? Well, tan theta, what is tan theta? 4 over 3, right? Yeah? So theta is going to, I'll write down what is theta here, is going to be tan inverse of 4 over 3. Arctan theta, how do you say tan minus 1? How do you say it? Arctan. Okay, it's the arctan of 4 over 3. Okay, so I'll write it down here. Okay, argz, which we'll call it, let's say, the angle, okay, is going to be tan minus 1 or arctan of what? Yeah, but the general case. In general. The imaginary. In other words, b over a. And we're not putting the I there. Don't put the I. If you put the I here, it's the calculator is not going to like you. He doesn't like to have I there. Right? There's no I in trig. Okay, so it's b over a. These are the equations. Okay, I'll just pause here and we'll do some examples. Okay, so we haven't actually finished that one. Okay, argz, okay, the theta basically, is going to be equal arctan of 4 over 3, which is
33,13.
okay, degrees. Okay, so we've got the module and we've got the angle. Okay, it's just trig, isn't it? Okay, I'll rub and we'll do one more example. Right, so I just want to do the same question with another example that we're not going to be in the first quarter, because the first quarter is the easiest. So I've got minus 2 plus 3i. Which quarter are we going to be here now? That's, first, second, third, fourth. Okay, right, the real part is negative, the imaginary is still positive, so it's going to be here, let's say somewhere like this. So that's minus 2 and that's 3. Okay? So, easy part is to do the modulus. That's always easy. How do we calculate the modulus? It's going to be the square root of a squared plus b squared. So, square root of? What's a?
4.
Yeah, okay, but I'll put it there like that, plus b squared. What is b squared? 3 squared, okay? Okay, and then if you can find that for me, 4 plus 9, 13. Square root of 13? You can leave it at that. Let's just keep it like that. Square root of 13. Is that right? Yeah. Okay. Now we want to find argz. Argz we know is tan minus 1. Sorry, I'm used to saying tan minus 1. Arctan of b over a. Okay.
3 over minus 2.
Okay, now here, let me just pause here. I want to ask you something. Yeah, no, we'll stay in degrees. Anyway, so I just confirmed with you, you guys are used to working with reference angle. What does that mean? You might think, okay, it just says tan minus 1 of b over a, so I can just put b, which is 3 over minus 2. But in trig, you usually work with a reference angle. So we always start with the first quarter. So instead of 3 over minus 2, we do 3 over 2. Okay? So I'm going to put 3 over 2. Now that's going to give me this angle. That's not the angle that I want, but we'll figure out what's the angle that I want in a second. So first of all, yeah, if you can tell me what's 56,3. Now this angle, I know, and I had to decide realize before that in my second quarter, if I want to go from this theta to the second quarter, then I will get, so I should really put actually argz equal. Okay, I'm going to start tan minus 1 of that, and then I know that argz is going to be equal 180 minus 56,3, which is equal
123.7.
Okay, all right. So let's just make sure you guys know how to do that. If I am in the first quarter, then it's just theta. Obviously, I don't need to do anything. If I'm in my second quarter, I'm going to do 180 minus theta, right? That's what we did now. If I get to the third quarter, what do I have to do to theta? You plus how much? 180. So if I was here and I knew I'm in the third quarter, I'm just adding 180. Okay, that's if I'm working with degrees. Okay, if I work with radian, it's pi. Okay? And then the fourth quarter, minus theta. So if I was here, then I just go to 360 minus theta. Okay, you happy with that? Yeah? we're almost done. Okay, so our last bit is to try and tie everything together now. So I've got one more example, z equal 1 plus square root 3 I. Now I'm going to save us, we're not going to calculate the modulus and the angle. You'll just take my word for it, but it's not difficult, okay? So I know that if this is 1, this is, let's say, square root 3. Now we can calculate the modulus, which is basically 1 squared plus square root 3 squared, all that square root, and it comes out as 2. You can actually see that it's the case, because 1 plus 3 is 4, square root is 2. That's pretty easy. Now, arg z, okay, is going to be square root 3 over 1, okay, or more likely, arctan of square root 3 over 1. And that, and I need you guys to be able to work with radians, okay, that's pi over 30. What is pi over 30 in normal degrees? You know?
Pi over 30.
3. So pi is worthwhile, remember, pi is 180. 2 pi is 360.
The answer is pi over 3.
Yeah. I did it quickly. I basically copied from the book, okay? But what I just want you to know, to be aware, what is pi? Is 60, okay? It's quite worthwhile remembering, okay? Pi is 180 over 3 is 60, okay? So now I know that this distance is 2, and this angle is pi over 30, okay?
So could we write like a little c in radians?
Yes, we should. How do we write radian? Don't we write, would you write a C?
A little c at the top.
The top, like this. I can't even remember. I normally, when I see, I just see rad. I don't know.
Yeah,
But if you see a pi, it's probably radians.
Yeah.
But there is.
Who knows why it's a C?
Yeah. We normally, normally you won't even write it. You just kind of need to be, okay?
No.
Okay. Now, what am I going to try and do now? What am I trying to do now? I'm trying to go from, we went from this, from the A and the B, we went to the angle and the modulus, right? What I'm going to do now, I'm going to take you backward. So we've got the 2 and the power of 3. I want to get back the 1 and the square root of 3. That's what we need to do. And that's this argand thing. It's basically representing the vector with these two angles. So let's just think about it. Okay? How can I get, what you need to remember that I've got a vector here with size is 2 and the angle is power of 3. How can I find this, which I know is 1, but how can I find that?
Cos.
It's cos, exactly. Okay? What is this, the real part? The real part of z. It's basically, or let's put it this way. The real part of z, that's the real part of z, divided by modulus z, is cosine theta, isn't it? So that means that the real part of z is the modulus of z times cosine theta, where theta is the arc, okay? Theta is arg z, okay? And in the same way, if I want to know the imaginary part of z, what will be the imaginary part divided by the modulus? What will that? That will be the sine theta. Again, theta is arg z. I'm going to make sure they can see that top bit. They do. Okay? So that tells you that the imaginary part of z is equal to modulus of z times sine theta. So that's like two equations that are worthwhile remembering. This bit. Okay? Specifically for this question, okay, the real part of z is going to be the modulus, which is 2 times cosine pi over 3, which we know is 60. And the imaginary part of z is 2 sine pi over 3. And if I want to do it, if I find that, cosine pi over 3 better be 1. And cosine pi over 3 times 2 should be 1, which is true, because cosine 60 is half. So half times 2 is 1. 2 times sine pi over 3 better be square root 3, which it is, because sine 60 is square root 3 over 2. So it does work. Now, how do we, what do we do with that? We can, that's the final bit here, I can say, that z is equal to 2 cosine pi over 3 plus 2 sine pi over 3. But I'm missing one thing. What am I missing here? Maybe you can find it. I'm going to pause. Okay? And Rachel, you got it. Obviously, I'm missing the I. I don't write the right I here when we started this lesson. When I want to know what's the imaginary part, I don't include the I. But when I want to slap it onto the complex number, I have to have the I. Okay? So if you put that in the calculator, okay, actually, there's one more thing that I want to do with that. Yes, they did it. Okay, z is equal, I can take a 2 out, right? So it's 2 times cosine pi over 3 plus I sine pi over 3. So I don't have to write the I again. And that is the final, that's the argand representation of a complex number. You've got the modulus here, times cosine angle plus I sine an angle. And that is really important. It's so important that I'm going to add it to my Hall of Fame of equations here. Okay? So in the general case, z, okay, will be equal to, okay, I'm sorry, I'm going to throw another letter in, but they use that letter, and it is a letter that's often there. So it's times r, or z equal r, times cosine theta plus I sine theta. Where theta, you already know what it is. I'll write it again. Theta is the argument of z, is the angle from the x-axis. And r, what should the r be? I didn't use r before, but you should know what r is by looking. What is the r? Is the modulus. It's the length of it's the modulus. It's the modulus of z. Okay, that really is the punchline here. Okay, yeah. You can write z. You see the two differences. Okay, this is where we started. Z equal a plus bi. That's like your component representation of z. And now we're using a different one, okay, where you have the modulus times cosine theta plus I sine theta. This is, you'll learn later in university, that's your using polar coordinates, something called polar coordinates. Very, very useful. Okay, I'll pause here.